Let me introduce the speaker. Dr. Reed Spray began her career in a small liberal arts college, a branch of the University of Virginia. In her junior year of undergraduate, she took both the MCAT and the GRE, unsure of whether she wanted to go to med school or to graduate work in chemistry. After touring, being a TA and job shadowing for a while, she decided that she wanted to pursue a career in chemistry, in teaching and research, and as a result, she graduated with a PhD in chemistry from Purdue University. Upon graduation, Dr. Reed Spray began a career in academia as a visiting assistant professor of chemistry at Smith College. For the last 2 years at Smith, Dr. Reed Spray has been working with his students, focusing on shape control and nucleation. I'm hoping I can speak.
No, that's right.
Density of copious oxide film for use in solar energy conversion. Last year, Dr. Reed Spray joined the ENC community and is currently an assistant professor of chemistry at ENC. We're proud to have her.
Thank you.
Dr. Reed Spray wants to continue with his work on shape control and nucleation density of copious oxide films, focusing on why shapes have different solar energy conversion properties. Dr. Reed Spray also intends to focus on the development of new electrode positive material for solar energy conversions. Aside from her research in chemistry, Dr. Reed Spray is also interested in other areas of research. Some of these research interests are related to what technologies can be brought into the classroom to help students better understand critical concepts in chemistry and related fields. So it is with great pleasure that we welcome Dr. Reed Spray to the Dr. John U. Free Physics and Engineering Seminar Series. The title of her talk is Studies on Copious Oxide and Delafossite-based electrodes for use in solar energy conversions.
Thank you. So I'm happy to be here today, and some of you may have seen some of these similar topics when I came for my interview, but a lot of the faces I see are new faces, so I think it will be new, and hopefully you'll clap just as loudly at the end once you've listened to all of the talk as well. I also have a surprise for you today because I just got finished working with a group of 11 Boy Scouts getting their chemistry science badge, and we did a little bit of chemistry magic and turned pennies into silver and gold pennies. So I'm going to pass those around towards the end of the talk so that you can see another avenue of electrode deposition. So one of the reasons that I focus on this work is because we have a huge global energy demand in our environment right now. We're going to be doubling our energy consumption by 2050 with an estimated 6 billion new energy users. So those are new energy users. Could be population growth. It could be new areas of the world that are not currently using energy, but they're going to be using energy in the next few years, and they're going to need some form of energy. And people believe that using only fossil-based fuels is going to be a bad idea. I'm one of those people, so I study things that could be not fossil-based fuels. One could be nuclear, one could be any type of renewable, so I'm not only just a proponent of solar, even though that's what my research is on, but I think that any renewable resource is a good avenue to pursue. So wind, water power, any kind of renewable sources are a good idea. And we need something that can be scalable and can be used worldwide. So it needs to be something that we're not going to run out of the materials. We don't want to develop something with some element that is very rare and hard to come by, because that's not going to solve our energy crisis. So because of that, maybe we'll have another slide. Because of that, I focus on solar water splitting. And I want to just describe that a little bit because sometimes people get confused about what solar water splitting actually means. And there are two ways that people talk about this. We can either use the power of the sun to actually store energy. And we store that energy in the form of chemical bonds. So you can split water into hydrogen and oxygen, and then that energy can be stored in those bonds until you want to break those bonds and release that energy. So that's one type. When you release that energy to electricity, that's where we're actually causing the sun to come in and release that, produce water again, and produce electricity. So the average American home uses, these numbers don't make as much sense until you think about what they can be represented by. So 31.2 kilowatts hour of electricity per day. You could do that by splitting water using 8 liters of water. So if you can imagine having 8 liters of water in a container, it's not that much water, and it's recyclable. So it's not like the water gets destroyed. It can be, you can store the energy, break that energy, release electricity, and then you have water back, and then you can cycle it over and over and over again. So the same 8 liters of water could power someone's home all day long. The other reason of why people care about the sun is because it generates a lot of energy. This current energy consumption could be, with our current standards, we would need to take up about the size, that number right there, about 48,000 would be about Massachusetts and New Hampshire area combined. So that's a pretty big chunk of land. There are some parts of the country that would say, okay, we don't need Massachusetts and New Hampshire, let's just have all solar power there and we'll just get that energy somewhere else. Or you can think of parts of the country where there isn't a highly populated region, and you could have a lot of solar panels there, and then if you could get that energy somewhere, then you could use it somewhere else. But that's one of the problems. So this talk will be broken up into about 3 different parts. One, I need to tell you what a semiconductor is, just in case some of you don't know, and why I use electrodeposition. Then I'm going to talk about the shape-dependent properties, and I'll end with the Delafossite type oxides, which are a pretty exciting material for solar energy as well. So just to start, I think most of you have seen something similar to this, especially if you're in some of the engineering classes. I think you talk about metals and semiconductors and insulators, at least I would think you have at one point, but you may not have heard all of these terms. So there's a metal and a semiconductor and an insulator shown here, and the average electron energy, or the Fermi level of the metal, is there's no gap. The difference between a semiconductor and a metal is you have a band gap. There's a split. So the electrons are not flowing freely here, right? In a metal, why do we say it's a conductor? Because it's easily able to flow electrons through the whole surface of the metal, right? Well, a semiconductor, all of the electrons are down here, similar to the HOMO LUMO, where you have electrons down here, and unless you do something to excite them, then they're going to stay down here. And so they're not going to go anywhere. Well, that's the same with valence electrons. The electrons that are in the valence band, they can move around in the valence band, but they can't jump up to the conduction band unless you supply some form of energy to them to do that. And so the sun is one way that you can make electrons go into the conduction band. Once here, we're going to talk about what these electrons can do. People often ask about why you can't use an insulator, and you can excite electrons potentially all the way up to the conduction band, but the gap is so large that it's not possible with the power of the sun, which means that it would have to be a pretty strong way to, I never like to say that you can not ever do something, because someone will theoretically prove that you can excite them, but in our current technology and with the power of the sun, you can't do that. The other thing we're going to be talking about is there is such a thing called a p-type semiconductor and an n-type semiconductor. The difference is that average electron energy of a p-type is going to lie within the valence band. For an n-type, the average electron energy is going to be in the conduction band. So when we talk about p and n-type, that's just one thing to think about. So this is one thing that you have probably all thought about when someone said solar cell. You think about the photovoltaics. The goal of this is to take the energy of the sun and directly convert that into electrical energy. So that's a direct conversion. There's no in between. You're not storing anything. You're not causing any other process to happen. You're connecting a p-type semiconductor and an n-type semiconductor, and you're able to turn on a light bulb or charge your cell phone or do any sort of electrical activity that you want to do. So it's able to charge something, it's able to convert that energy into electrical energy, which is what we use. So that is one type of solar energy conversion. That's not really what I do, although the materials that I make could be used for that, but currently I'm not combining them and making a photovoltaic. What I care more about is creating some sort of electrochemical cell. So this goal is much different. You want to drive a reaction, and you want to use the energy of the sun to actually drive a chemical reaction. The reason we care about this is because if we want to take one land mass and we want to just make a bunch of hydrogen to then be used and produced for energy, we would need something that can generate a fuel generation. So something like producing hydrogen to be used later, or CO2 reduction, or being used in catalysis. So this is a different process because we're not instantly using it and having to use that electrical energy at that moment. If you don't use the photovoltaic electrical energy at that moment, you have to have some sort of battery or something that can store that electrical energy for a later date. If you're generating a fuel, then you can use that fuel whenever you want to use that fuel. So that's the main difference between the two, is that one produces electrical energy that is needed to be used immediately or stored in some battery contraption, or the other is you make a fuel and you use that fuel when you so choose. This again is just showing you how a p-type and an n-type semiconductor would work once you are illuminating that with either light from the sun or with a solar simulator, which I'll show you a picture of later. So with an n-type, what happens is when the light comes in, you end up, holes are generated, and we're using those holes to make oxygen. And then on the other side, on your metal counter electrode, that's where you're actually producing the hydrogen. So the n-type is producing the holes that produce oxygen, and unlike the n-type, the opposite process happens with the p-type. So the light comes in, you produce the hydrogen. On the other side is where you produce the oxygen. So that's the difference. One will produce hydrogen directly, and one will produce oxygen, and then you need a counter electrode to produce the hydrogen. So that is why people have been more focused on making new p-type materials, because if you could we don't really need to produce oxygen to make a fuel. We want to just produce the hydrogen. And so if you could have a material just produces hydrogen continuously, and you could use that hydrogen, then you could use that as a fuel source. So what are some other things people care about? Well, this figure, people would say, oh, well, it's easy then. Just make a p-type and an n-type semiconductor, and we've solved the world's energy crisis. It sounds simple, right? But no material currently can do that process by itself. So that's because of these band positions and how they have to be very specific to drive the production of hydrogen and the production of oxygen. If you see this dotted blue line here, that's the position that the valence band needs to be below in order to drive the reaction to produce oxygen. And your conduction band needs to be above this red dashed line to be able to produce hydrogen. So when you look at this, there's not really very many materials that cross both of those barriers, right? With the red bars being the conduction band and the green being the valence band. The only one that really, or the two that cross both, are zinc oxide and titanium dioxide. Have you seen titanium dioxide before? What color is that? You've probably eaten it before. It's in your powdered donuts. So the white powdered donuts, that has titanium dioxide in it. So if you like those donuts, you're eating titanium dioxide. The other thing that it's in is white craft paint. So it's used in a lot of pigmentation. When they stopped using lead, which gives a white color, they now use titanium dioxide in white pigments. So that's a white color, which means it's not very good for solar energy conversion because of this next slide. So not only do you have to split the bands in a very appropriate region and need to be positioned right, but they need to be able to use the power of the sun. When you look at this here, this is titanium dioxide. This is how much of the sun it can actually utilize. Pretty pitiful. There's not much there. So that means that even if you have a lot of titanium dioxide, its efficiency is terrible. And so it's been used in some photovoltaics, but They have to use a lot of dyes, and they have to couple it with things, and they have to use a catalyst and a lot of other things that may not be inexpensive, so it's not necessarily the best. One that I've worked on a lot, one particular reason is the band gap is lower, so it's about 2.1, and it can utilize a lot more than titanium dioxide, so that's good. We're already improving how much of the sun we can use. And another material that I'll end with is copper iron oxide, and it can use even more of the sun. And really, this portion is unusable because of the band position. So we're about at the max efficiency when we're here, because you need 1.23 eV is the split between the hydrogen position and the oxygen position. So you can't really be any smaller than that, which means that if we're in this region, if we're using all of this, that's the best we can do. We can't do any better than that. So this, in a way, is the most efficient material you could make. It needs some more studying on it to be a more efficient material on its own, but it does have the capability of being a great material. So why do we use electrodeposition in my lab? Well, one, it's how I learned how to do these synthesis mechanisms that I have studied for 5 years, so that I just teach that to other people, but there's many other reasons than that. There's a huge literature base. There's also, it's very low temperature, so a lot of synthesis of inorganic materials involve really high temperature synthesis. They put it in a tube furnace, or they put it in a box furnace, and they have to heat it up to 1600 Kelvin, really hot. It's not something that could be scalable. If you're going to have to use a lot of energy to make something, then that doesn't really, it kind of defeats the purpose of making something green if you have to use a lot of energy to actually make that green material. So you have to think about cost analysis for that. The other thing is it's very easy to make, and it's relatively inexpensive. It just involves a 3-electrode setup. You just need a working electrode, which is where the process of oxidation or reduction is happening. Whether you want it to be oxidation or reduction, that will depend on your system. And then the counter electrode is just where the opposite process happens. And then the reference electrode is just there to help you keep those potentials consistent. So that's how I make all the materials, and the people in my lab make all their materials. And the other thing that I've worked on is this shape control. So we found that shape actually matters in solar energy conversion, and one of the ways that we've done this is by changing the shape of something. It used to just be cool enough to change the shape of something, and now you have to make it useful, right? So you first start out a process and you're like, ooh, I can make all these different shapes, and that's cool, and then you get to publish lots of papers on that. And then you have to convince people that you actually did that for a reason and not just because it was cool to see all the different shapes that happened. So we studied the mechanism of why this happened, and we believe that there's a high energy phase and a low energy phase. And the way that it grows is it grows to the existence of the higher energy phase growing out of existence. So you can put a barrier on your crystal, which really isn't a barrier, it's just in solution with your other materials, and you can change the high energy and low energy phase, which means that instead of it growing to be a cube or a rectangle, it grows to be an octahedral or a triangle shape. And so I'm going to show you that you really can do that. And at first people were like, oh, that's cool, but why does that matter? Well, it matters a lot because of how copper is arranging in these different shapes. So you can, if you have a cubic or a 100 face, copper arranges in this manner, whereas in the 111 they arrange in this manner. And that might not seem like that big of a deal, but depending on where it is on the surface or how things are terminated or how they're interacting, that's going to change all of these things. It's going to change the interaction on the surface. It will change the efficiencies of hydrogen and oxygen evolution. It can change the flat band potential. It can change the amount of photocurrent that comes out of your system. So it does a lot. And we know it does a lot of these things, but we don't know why it does any of these things. And so I've focused a lot on how it does change things and how it can be better. And now I want to, while I'm here with my students, I want to figure out why it does things more efficiently so that we can maybe tailor a material that can do it very specifically. So copper oxide, most of you have probably not seen crystal structure patterns unless you took inorganic chemistry, which I don't think many of you have. But crystals arrange naturally in one way. So every substance that you look at, it can have a certain arrangement. It's going to be that way no matter what. Even when gold arranges, or when diamond arranges, or when graphite in your pencil, all of those are crystal structures. So the only thing in graphite, which is in your pencil, and the only thing in diamond is carbon, right? But how that arranges changes whether you're going to be writing on your piece of paper or whether you're going to be wearing that in a piece of jewelry. And so the structure matters, and it's the same thing for semiconductors. So they all have different structures. And it just so happens that this is copper oxide structure. Oxygen is always coordinated to 4 coppers, and you can't tell in this picture, but in this one you can. This copper is always coordinated to 2 oxygens in a linear format. So it's tetrahedral around the oxygen, and then it's linear between the copper and the 2 oxygens. And we've already talked about how it has a good band gap. It can be P or N type, which I don't think I had mentioned. It's low cost, and it's low toxicity, and it's very abundant. So we're not going to run out of this material, so it would be a good way to do it. The other thing I want to mention about this is it's scalable. So we talked about at the beginning how we can make materials, but if we're making them from something that's really expensive or something that you can't make a lot of or it's hard to make, then it's not going to do you any good. And electrochemistry is very scalable. That's how they put paint on your cars. That's how they put paint on a lot of metal surfaces. So the lockers in the gym, potentially even the paint on these chairs were probably electrodeposited. All you have to do is have some sort of conductive material in a bath. Your bath can be as big as this room, or it can be as small as this cup. So it doesn't matter how big or small it is. So if you could make an efficient material with electrochemistry and you wanted to take that to industry, you could, because you can then, and engineers care about this. Chemists don't always care about this, but engineers do care about this because they think about how you can scale it up, how you can turn that into an industry, how you can make money off of that, and how you can change the energy crisis problem. So this is an example of something that you could. If you're making something with a really tiny contraption that is really expensive, scaling that up to a large scale to make a difference in the world is not going to happen. Electrochemistry, you could. So that's how we do it, and this is to prove to you that you can actually grow them in different mechanisms. The only difference between my cubic bath and my octahedral bath is I add SDS, which is in a lot of the soaps that you use. It's just a surfactant. It wouldn't have to necessarily be SDS. In fact, we tried Palmolive, like dishwashing soap that we washed our dishes. We put that in, and it also created the octahedral shape. So it just needs to be some sort of soapy surfactant type mixture. It's just we didn't know what concentration was in the dishwashing soap, so we used SDS so we could actually change the concentration and study properties. So this is an SEM image, scanning electron microscopy, and this is how we tell the shapes. So cubic, you can tell they kind of all look like little cubes, and octahedral kind of look like, depending on how you look at them, pyramids. 2 pyramids on top of each other would be the full crystal, but sometimes depending on how they deposit, it might just look like a pyramid structure, and so that's the difference between those 2 surfaces. But we can do more than that. We can make cubic, we can make truncated cubic, we can make cube octahedral, we can make truncated octahedral, we can make any shape and variation of the 111 and the 100, and we can also throw in a few other like 110, which isn't shown in this picture. The only difference between all of these is how much of these extra additives we put in. So how much surfactant and how much chloride we put in, because those stabilize different faces. So people thought it was cool, like I said, for a while. Then we made all these pretty shapes, and pure mineralogists thought you couldn't even, that's not even possible. Like, how can you make a shape that isn't this cubic structure? Copper oxide is always cubic. That's crazy. So they were really impressed by that. But what we were actually impressed by was that it matters. If you look here at this figure, photocurrent studies are just shining the sun. So we have a simulator where we can simulate one sun on our material, and some of the students in this audience are working with me in instrumental analysis, and we're building a solar simulator right now, which is pretty fun. So All you have to do is shine the sun on your material, and then you can see how much current or photocurrent you are producing from your semiconductor. So in this case, the scale, I don't know if you can see it, but it's only 0.02 milliamp per centimeter squared. This is 0.2, so a tenfold increase. Now, neither one of these materials are earth-shattering. The 0.2 would be about 0.2% efficient, which is not really... When you think about efficiency, you want better than 0.2%. But we're making progress because we've already doubled, not only doubled, we've already tenfold increase from having cubic to octahedral. So now there's hope, because what if these could be improved by making them smaller? Or what if they could be improved by making them a slightly different shape? Or what if we could improve it by pairing it with another material and putting a catalyst on it? So people have not really gotten a blank semiconductor to be any better than about 1% to 2% efficient, and then they just add all sorts of other catalysts and other things on top of it to get to about 12% efficient. So if we could get this from 0.2 to 1 up here, if it didn't die out, if it stayed up here, then that would be a pretty good material for a photovoltaic device or for electrochemical cells. And all we did here is change the shape. So that's pretty cool. And I care about why. So when I was in graduate school, I already knew this. I knew that we could change the shape, and I knew we could get better properties, and that was awesome. But I wanted to know why. Why can you change the arrangement and it has a different property? Are we really causing this change based on the arrangement, or is there something with the additives being incorporated into the crystal? And so that's what I want to focus more on, is figuring out why this is so much better. Why is there a tenfold increase? And if it is, in fact, the copper arrangement, can we change it to another arrangement to make it even better than that? So when I was at Smith, I worked with 4 different students. This slide only shows 3 different students' work, but we need to take the film and make them a very densely packed film. The reason for this is when we're studying different properties, we want to make sure we're actually studying the properties of the crystals themselves and not just of the background or of something that is on the conducting slide that we put them on. So an electrode, we deposit on these conductive electrodes, and if we don't cover the whole film, so this one doesn't cover the whole film, and you can see ITO in the background. This one also doesn't cover the whole film. This one does, and they're really tiny. The smaller the crystal, the better the photocurrent. And so that is what we did with octahedral. We got pretty far with cubic, and we didn't get that far at all with truncated. So this summer I'm going to be working with more students, Chris and Carrie, which I'll show you at the end. And they're going to be taking off from here and trying to make the rest of it done. And then we're going to do lots of other studies on these. So what else we did with this while I was in graduate school is we wanted to see if we could selectively block things. So one thing that people spend a lot of time and money on is they want to selectively put something on a surface. And they have to create these masks. They actually create polymer masks, and they stick them on, and they protect sides, and they do all of this really expensive technology to mask a surface. So we thought, what if we did this with solutions? What if we could, since we can selectively absorb something on a surface, what if that selective absorption can actually block the deposition of something? And so we proposed that we could selectively deposit on the 111 and selectively deposit on the 100, and then we tested that out. So my part of the project was I wanted to see if we put SDS in solution and we have gold in the solution as well, can we electrodeposit gold just on one plane? Can we put it just on the 100? So that's what we hypothesized based on our synthesis conditions, and we ended up getting X-ray XRD, which is X-ray diffraction, where you can see the crystalline type. So I have indium doped tin oxide, copper oxide, and gold. So we knew we had deposited gold, and then we did SEM to prove that we had deposited selectively. So if you don't have SDS in your system when you're depositing gold, it goes everywhere. And I don't know if you can see the little tiny particles in the back, but this is gold deposited on our copper oxide crystal. When we put SDS, there's no longer gold on any of the 1-1-1 planes. So it did, in fact, do what we thought it would do. It selectively blocked. And this was a huge deal because people were spending a lot of money putting masks on and then taking masks off, and then they had to worry that they might have damaged their crystals in the process and that maybe they wouldn't have as good of properties anymore. So if you could transfer this to another material, then it would be really earth-shattering, because then you could say not only does it work on copper oxide, but it works on any material that you can deposit something. And so then I told this to my lab mate, and hers was selectively blocked with chloride, so that's how she made her crystals. And so she tried it with chloride, and in fact, when you didn't have chloride, it went everywhere. But when you put chloride in her system, she didn't have anything at the tops of her crystals, which was beneficial because your light coming in, you want it to be able to hit the semiconductor surface, and you want it to be able to work with the catalysts that are on the planes of the crystal. So this was really a cool thing, and it also meant that other people could take my method and transfer it to other methods, and it's not just one way of doing something. And anytime you're doing science, you want to make sure that not only it works for your system, but it works for someone else's system, and everybody else can reproduce what you're doing. So that's what we did. So in conclusion for this part, without SDS and with SDS, you get a very different film, and people liked the way that this looked. And when we published a review article about this process, I got to be the cover picture, which was a pretty big deal. So I always try to highlight that. So some of the students may know what Material Research Society is. They always have it, the fall meeting in Boston, and so we got to publish in this journal, which was great. The other thing I did with this is I wanted to see if you could photo deposit selectively. And so first, when I showed you the previous one, we were electrodepositing gold. So we were taking gold cations in solution, reducing it to gold metal on the surface. This is the same process, except for instead of applying a potential to reduce it, we wanted the light to do that. We wanted the sun to do the reducing. And we thought that it would selectively reduce only on the surfaces that were creating electrons, because you need an electron to be able to go from gold 3+ to gold metal. So we thought that's where our gold would go. And in fact, we were encouraged at first that the gold did go there. And then I tried probably 50 other substances, and they all went there. So they all went on the 100 plane, and some of them should have been oxidized, so they should have gone on the 111 plane, because that's where the photooxidation would take place, where the holes are generated. So this was discouraging for my advisor, but it was very encouraging for me, because I wanted to know why that happens. If we're always going to have something on this plane, then what is on this plane that is always blocking a deposition? There should be deposition everywhere if there's just nothing causing those. So if it's not electrons, or maybe it is electrons, but they're being masked by the SDS that's still on the surface. And so we did lots of treatment methods of trying to get all the SDS off. And that's where I want to pick up with, is seeing if we wash this film for 2 months, and then we do analysis, is the SDS still there? And if it is, that probably means that it's somehow incorporated into the crystal and is not being washed away. And that will tell us more about what we're getting. So this is just to show you that even when I deposited what should have been, so lead oxide should have gone on the one plane, it didn't. Everything went on there. And the platinum, I mean, you can tell how selective this is based on, this picture's a little bit dark, but it just keeps getting thicker and thicker. It does not want to touch the 111 plane, which means that there's something there that is really impeding that. And I think that's an interesting phenomenon that I want to look into more in the future. So that's the end of all of my shape control, all of the copper oxide selectivity, and all of the changing the nucleation and selectively depositing gold and other catalysts on the surface. So I'm going to switch gears just a little bit, but not that much, because I stuck with copper still, but into a Delafossite material. So ternary oxides have been interesting to people because you can change a lot of properties by adding another metal into your system. So instead of just having copper and oxygen, or instead of just having zinc and oxygen, or titanium and oxygen, you can have silver and copper and oxygen. And there's a little bit of dynamics that can change from that. Or you can have platinum and copper and oxygen. Or you can have anything that you want in these sites. So the only criteria is that you need to get something in the A site, which is all of these red spheres. It has to be a 1+. In the B, it has to be a 3+. So those are your only, that's the only thing you have to worry about. So you can have silver here, or you could have copper here, or you could have manganese, you can have iron, you can have cobalt, you can have anything you want in those sites as long as they can be in that oxidation state. So people care about this because most of them theoretically have been proven to be p-type, but no one had studied, no one had made these and studied the photovoltaics of these devices or the electrochemical cells of these devices, and two, very few of them had actually been made at all. It was kind of people were looking for other semiconductors to make, and they were like, oh, no one's made ternary structures, let's start making a bunch of ternary structures. And so people started making them in tube furnaces, like I said, with really extreme temperatures for really long periods of time, which would be not an energy gain if you made them that way. And so we thought, what if we could electrodeposit them? And no one had ever electrodeposited any Delafossite structure. So I wanted to be the first one to do that. And so that was my goal. My last year and a half of graduate school, my goal was, I don't care what Delafossite material I electrodeposit, but I am going to electrodeposit a Delafossite material and write a paper on that. So that was my aim, was I want to be able to do this, and I want to be able to study its properties. So I want to be able to know, is it actually p-type? Is it any good? Does it have a good band gap? Does it have a good band position? All of these things matter when we were talking about the first couple slides of it has to go over both the hydrogen and the oxygen production. It has to have an appropriate band gap. It has to be able to utilize the amount of sun we want. We would prefer it to be p-type so we can use it in an electrochemical cell and produce a bunch of hydrogen. So those were all things that we wanted to do. So I liked copper because I had worked with copper for a long time, and I was comfortable with copper. I knew how it worked. I knew how it would behave electrochemically. And so I thought, well, I'll just start putting things in with the copper and see if I can get a film. So the idea was we were going to do all of the chemistry with copper. We were just going to take copper 2+ and reduce it, and we were just going to have a 3+ in our solution, and it would just somehow get incorporated into that formation, and we would magically have our structure. And that sounds great, but if you've looked at any of the solubility properties of 3+ metal cations, any of the chemists in the room, are they very soluble at very many pHs? No. So you put a 3+ metal in with your copper and you crash out all sorts of things. So there went that idea. So now we had to think about, okay, can we co-deposit based on doing 2 redox processes with the same potential? So can we both oxidize and reduce in the same bath? That seemed like a crazy thought, but you know, what grad students do lots of crazy things, so I thought I would try it out. And I picked manganese because I knew manganese very easily went to lots of different oxidation states, so I thought if I had to pick something, this would be my best bet. It also was the most soluble at lots of different oxidation states, so I thought I had the best shot with that. And I did in fact get a film. The problem is that I actually was able to produce the manganese very easily, but the copper didn't want to be reduced at the same time. So it decided it was going to stay as 2+ while the manganese went to the 3+. So that structure is actually perovskite. So when you annealed these, which I'll show you a picture of, that actually forms perovskite because it's formed that way amorphously. But something magically happened when we annealed in argon. So without extra oxygen in the tube furnace, we were able to reduce the copper and keep the manganese in the 3+. And then that also took away one of our oxygens because it was so oxygen deprived when you're flowing argon through your tube at really high temperatures. So that was encouraging because we could prove that there were crystalline, and I'll show you XRD of that. And then these are just SEM to show you about how thick they were. They were about 430 nanometers thick, so not that thick, and they have a pretty uniform film, so we thought it was promising. I didn't get to electrodeposit Delafossite, but I electrodeposited perovskite, which not many people have done, so I was like, we're almost there. We might be able to make some waves with this, but I still wanted to do more, and this is just to show you some EDX spectrum. This gives you your composition. This proves that we did have as to positive 1:1:3 ratio, meaning that it was more like the perovskite structure, and then when we annealed we got the perovskite and the Delafossite. So that was just to show us that, because XRD can only see crystalline materials, so we had to use EDX to show us our ratios of copper and manganese to oxygen, because that can look at non-crystalline materials, so you can just get elemental ratios with that. XRD, again, I got perovskite and Delafossite, so it was pretty encouraging. And then I did some band gap measurements, and that was also encouraging because I was getting a band gap near where it should have been, in about 1.55. So that was nice, and it had band positions that could do the hydrogen, not necessarily the oxygen, but that's okay because we just wanted a p-type material anyway. So all of this was very encouraging, and you would think you're getting like really excited for like something earth-shattering, but unfortunately the earth-shattering result was that it reduces when you shine the sun on this material. So the material itself is just not stable in the sun. So it photo reduces. That's what this huge peak is here, is it's reducing itself. And you can't have a stable material that you shine a bunch of sunlight on to produce energy if at the same time as you're producing hydrogen, you're also destroying your film. That's not very cost effective. So although that was slightly discouraging, we did learn a lot about the process, and we learned that it is possible, and it does seem that the theory is going to match the results, but we're just going to have to find materials that can have good properties and match the results of the theory. So then I switched to iron, because iron is also very abundant. I was trying to use these transition metals that are not going to go away. If you're going to make something, you need to make something that's going to last for a while and people aren't going to run out of it. So I did the traditional. This time I had to switch to an organic solvent, which in my aqueous love of chemistry, I like to stay away from the organic solvents, and I had to use DMSO. I know. I know that hurts Dr. Williams' feelings, but I had to use DMSO, which to me was a big deal because that's like a scary organic, right? That's not even just like an acetone or an ethanol. It's like one that can take things through your skin and really be harmful. So I thought I was a real chemist at that point. I had to do that to be able to, graduate as a real chemist's work with some scary materials. So that's what I did, and that was so that the iron would stay in solution, because like I said, they weren't soluble in water. So that's what helped me get them to be in solution so that I could focus on the copper chemistry, because that's what I wanted to focus on to begin with. So when you do that, you can reduce the copper 2+ to 1+, and the iron stays as 3+ because we weren't going to reduce that, and it wasn't enough of reducing power for that. And I did get amorphous Delafossite, so that was a big deal because the ratio of as deposited, I actually deposited a Delafossite structure, it just wasn't quite crystalline, and with a slight annealing, I was able to keep it in that Delafossite structure and make it a crystalline material. So we proved that by showing the EDX spectra was a 1-to-1 instead of the other ratio that we were using, and my annealing is, you can see these very small, not very sharp peaks of copper iron oxide. So this is where improvement needs to happen. Even though I did deposit a Delafossite structure, it wasn't crystalline as deposited, and it's not even that crystalline once you anneal it. So there needs to be some, this was towards the end, I was trying to write, my thesis and graduate and find a job and leave, so I didn't get to focus as much attention on this, but I think there's room for improvement on making this a better material, or finding another material that you can electrodeposit that might not have these same properties. But even still, with it not being that crystalline, we got a good band gap. We have good band positions that this can actually do both, so that's encouraging because it could actually produce hydrogen and oxygen, which is a great thing. And then when our final test, I know that you're on the edge of your seats, we actually didn't photo reduce our film. We got a pretty good amount of photocurrent, the same amount. We were seeing that 0.2 with our copper oxide in its best, most efficient, utilized way that we could possibly make it. And already with like not much effort being put into detailing in on how to make this structure in the best possible way, we're already getting the same efficiency as the copper oxide. So that's encouraging. and means that likely with some improvements and further study that we could get even better efficiency, hopefully up to 1 to 2%, and it is p-type. So in conclusion for this part, you can both electrodeposit perovskite and Delafossite, and you can get p-type materials. And I didn't show in this slide, but they actually, after I left, they continued on with the copper iron oxide, and they were actually able to detect hydrogen with a GC. So it does produce hydrogen. They had to do some fancy studies for that, and so that we ended up getting to publish that, but they had to purge it with a bunch of argon. They had to do a bunch of things to the system. So it's not that great, but like I said, there's a lot of room for improvement, and that's where we like science to have need for improvement. Otherwise, there's nothing for us to study. If we had all the answers already, it wouldn't be very fun. So I'm excited by the fact that we don't have all the answers for why shapes change properties, and we don't have all the answers for how to make these Delafossite structures be efficient solar energy converters. So there's lots of room for me to study over the next 25, 30 years to figure out all of these things, and I'm very thankful for the students that have studied with me in the past. Maddie and Arish and Jenny and Lauren were the ones that I worked with at Smith College, and I'm also very excited to be working with 2 students this summer. So Carrie and Chris are going to be working in my lab this summer, and this is a picture of how simple the 3 electrode setup can be. So we just have these alligator clips and we hook electrodes in, and my instrumental analysis students got to use the soldering iron and make these alligator clips hooked to wire, so they felt like they were maybe a little bit like electrical engineers for a day. And then this is the solar simulator, which is not quite set up, but we're making progress. And so once we have all of that set up, we'll be able to make materials and then study those materials for their properties, and I'm excited to continue doing that. So maybe next time I talk, we'll have even better results to share with you about those materials. And I always like to thank my graduate advisor, Dr. Kyung-Shin Choi, and I went to Purdue, so I'm a boiler maker. There's lots of good engineering programs there, so even the chemistry people, they're a good chemistry department, but the engineering department is great there as well. And the people that helped me on this project and my former lab, and I switched this to a Wisconsin Badger because my advisor, Kyung-Shin Choi, she got recruited, and they stole her away from Purdue, and she's now at Wisconsin Badger, which is a Big Ten rival. So that was, a sad day in sports, but it was a great decision for her, although I think they're better in sports as well. And she is now in the Wisconsin chemistry department, and there's a lot more material science chemists in that department. She was the only one at Purdue, so it's a good move for her. So if you're ever interested in going to graduate school in this field and working with her, I could give you some recommendations and contact her for further information. And with that, I'd like to end with any questions you have and pass out another area of electrochemistry, which I worked with the Boy Scouts today. So I'm going to let you pass these around. And we practiced alchemy in a way because we turned pennies into gold and silver. I need these all back because they're really gold, so I'll be collecting these, but if you can pass those around, you can show. I'll pass that back. So all you have to do with that process is, if you have copper, so they should be passing them around. So copper is a metal, right? And copper's in penny. So you can electroplate zinc metal on the penny in a bath that's heated up, and that's what the silver is. Then when you take that out and you rinse it off and you put it on the hot plate again, it forms an alloy with copper and zinc, which is brass, which appears to be gold colored, but is not in fact gold. So these are worthless pennies. In fact, I don't think they'd even accept them as a penny anymore because you have coated them with zinc and brass. So I'll take those back when you leave, but I'll take any questions either on the pennies or on my research. And thank you for your attention. Either.
So it seems to be so much work before you can see whether or not these things have good.
Well, the depositions happen in like 15 minutes.
Okay.
So in a day, you could deposit 15 films, go test the XRD and SEM, and the next day do the photocurrent. So in 2 days' time, you would know if the film was good or not.
Okay.
Yeah.
So one other thing I was thinking is there any way to do all of this in simulation mode without actually having to, can you have some sort of program that can go through a series of suspected material that you can start using?
Yeah, so no one has really done that. I wish I knew more about that. I don't really know much about like computer simulations of those, but I think that you probably could based on electronic transitions and how favorable something would be. That would be very interesting to study. Also, I think you could do some simulations with the copper arrangement and how the surface could terminate differently, because I don't think that, I mean, it's still copper oxide. It still shows up as copper oxide. It hasn't changed the crystal structure type. It's just changed the arrangement, which means that instead of having copper at the surface, you might have oxygen at the surface. What if oxygen is more reactive, and that's why it's better? So if you could tailor it to where it's all oxygen on the surface, you might have even better. So I think you could do simulation, but I don't know how to do simulation. So someone else should do that and tell me. Yes.
I have like 5 million questions. I'll just save like 1 or 2.
Okay.
But, what does when you're depositing on the different faces, your shapes, what specifically goes on between the SDS and the chloride that causes it to selectively deposit?
So we don't really know. All that we really know is that for some reason, SDS wants to block the 111 plane. As far as the deposition bath, we think that it's absorbing on the higher energy phase and causing the higher energy phase to switch. So that's all we know about that. But there's no mechanism. That's the other thing I would like to know is it really just absorbing, like we've hypothesized and said in the paper that we wash it all off, or is it actually being incorporated into the crystal structure? Because there's a possibility that sulfur could be incorporated. What if the reason it's better is because there's a slight doping of sulfur that we can't detect on the surface, and that could change the properties, which is a possibility because all of them have sulfur groups at the end. So there's a possibility that you could be incorporating some part of that SDS in there, and because of that it just won't allow anything else on that surface. Or it could just be that we weren't washing it very well. But I mean, we did some pretty extensive washing studies and we still see it. I want to do XPS, which is it allows you to see the oxidation state of the elements, and so it's a surface phenomenon. We'll talk about it in instrumental, but because it's a surface phenomenon, it will just tell you what's at the surface. So what if it's a different oxidation state at the surface, and that's what's causing the enhancement, and that oxidation state only happens when there's SDS? I don't know, but we'll find that out from that.
Like you discussed that you use the SDS just so that you could like vary the concentration and see the effects. Like what were the effects there? What did you see any trends?
So if you don't have enough in there, you don't get the full octahedral. That's how you get the varying shape. So you can get more of the truncated shape by not having as much SDS. If you don't have enough at all, there's like a critical point that's needed to even change the shape. So if you have a very small amount in, it'll still be cubic. It'll just be there and be soapier. But if you have a certain critical point, then it becomes octahedral, or any point in between could be one of those varying stages of truncatedness. Yeah.
What are the variations did you use?
What are the what?
What variations of SDS did you use? Anything else?
I mean, do we use any other additives?
Yeah.
So we used SDS. That's the other thing, because there's SDS when it's in a sulfate, but I wonder if the same thing would happen with sulfite, and there's different states that we didn't use any other things. We did use other additives. We used nitrate, chloride, perchlorate, a few other just different things that we added in, and it didn't seem to give you any better shapes. I think that ammonia gave you another shape, but it caused these like it was, I think it was kind of eroding the crystal at the same time because it was basic, so it was kind of eating away the crystal, so you had like a rough surface, and it wasn't as good for that. But yeah, I don't know. I think that there could be, I've seen some papers where they've studied reactivity based on it being a sulfite or a sulfate, or all these different ending terminals could change how it interacts with a glass surface. So if it can change how it interacts with that, it might change how it interacts with your solution that changes the properties. I don't know. I mean, those would probably also be good simulation studies that I don't know anything about.
But you don't have a large sample space of material that you can start with when you show your chart where the bins are, right?
Right.
You can only use the things in the middle there, right?
Mm-hmm.
So you don't have a whole lot of
Right.
things to try. So did we ever find out why Delafossite was disintegrating under excitation by the sun?
The manganese one? It just must, it could be that it's just my synthesis mechanism of the manganese and it's just not stable and there's a photoreduction on the surface, or it could be that all copper manganese oxides are unstable. We didn't really look into it. It didn't do what we wanted, so we gave up on it and moved on. Yeah. Other questions?
Mike has a question.
I don't have a question.
Okay, I have another. I just wanted him to ask one because I don't know. So the example that you gave for the deposition, like you were using the gold ions to deposit on there. I guess first question, like what other things did you experiment with depositing on? And also, is there a selectivity of if you had a mixture of ions in solution as to what you're depositing, or would it just deposit everything?
So photodeposit or electrodeposit?
Yes.
Well, photodeposit, I never had more than one thing in solution at a time, so I guess that could be something you could look into, as if you had two. But then it would be difficult to prove what you had and where. I mean, you could do EDX and do a, like, look over just one area and see if it was only platinum here and it was here. But if they were mixed together, like if you tried to put gold and platinum in solution and then you shine the light on it, if they both still went on the 100 plane, you wouldn't really know which was which, right? Unless you did some element mapping with EDX. But with the electrodeposition, everything has a different reduction potential, so it would deposit as it reaches that point. So it wouldn't really make sense to have more than one thing in there because you'd have to do several different potentials for that to happen. And those things happened within like a second. I mean, you could electrodeposit gold in less than a second.
One last question. I see that you've annealed with, what was it, argon?
Mm-hmm.
So, did you just use the natural property of argon to create an annealing schedule?
So the reason we were initially using argon is because it's supposed to be inert and not cause any changes. We didn't see that was the case with the manganese system, but we did see that that was the case with the iron. It didn't seem to do anything. People have also annealed with other things. So you can anneal with hydrogen sulfide and you can sulfur dope, or you can anneal in the presence of ammonia and you can nitrogen dope. So you could anneal with lots of different things, but we were picking argon to try to keep the oxygen content the same and to keep everything the same, yeah. Yes?
I'm sorry, I'm not quite clear on the definition of annealing. Could you?
Annealing just means heating up. So it can be like a box furnace where you just turn it to 500 degrees and anneal it for a couple hours. Annealing is just a term of heating up. And you can heat up in the presence, if it's a tube furnace, then you just have a tube that's sealed off from the environment with all of these. I actually built a tube furnace in graduate school so we could control it more detail. And you have to have all these like fittings and septums and different things. So you can flow a gas or you can flow nothing. You can have it open to oxygen. You can flow, like I said, you can flow the hydrogen sulfide. You can flow ammonia. You can flow anything through it. And you're just heating up a ceramic plate that then heats up the tube that your sample's in. So that's all that is. So it just means not a hot plate heating up, or a Bunsen burner. It's in a concealed tube so that you are controlling environmental aspects. Nathan, you have one more question? You can come up after if you want.
Let's thank the speaker one more time.
Thank you.